Okay, 410 nanometer light. This is, by the way, intense, almost ultraviolet, right? Falls on a slit that is, well, single slit, 0.032 millimeters wide. What is the full angular width of the central diffraction peak? Well, remember that the central peak is doubly as wide as these other peaks are. Okay, so it goes whoop, and then we get minimum here when sine of theta is lambda over d. Okay, so lambda is the wavelength, d is the how big the slit is, right? Okay, and then you get one at 2 lambda, 3 lambda, etc. Okay, and I kind of cling to this thing, right? Okay, so the full angular width of the central diffraction peak is going to be the sine of that angle is going to be, it's going to be twice. Well, let's figure out this angle here, okay, and then we'll just double that. Okay, so the sine of this theta here is going to be lambda over d. Okay, so the theta is going to be half of theta, right? I'm figuring out this half of the theta, right? Half of theta is the inverse sine of 410 times 10 to the minus ninth meters, that's nanometers, right? Divided by d, which is 0.0320, and that's millimeters. So it's times 10 to the minus third. Okay, so let's, half of the angle is, we can do this. I don't know why I do that. Okay, I think I just don't trust myself. So I'm going to do half the angle and then multiply by 2. Okay, so inverse sine of 410 times 10 to the minus ninth divided by 0.032 times 10 to the minus third is 0.734, and then that's degrees, multiply by 2 is equal to 1.468 degrees, or 1.47 degrees, right? Okay. Now I'm making it awfully hard for myself. Really, all we have to do to get this in radians, literally, is just go lambda over d, right? So half the angles, this is degrees, right? Okay, half the angle is just literally 410 times 10 to the minus ninth divided by 0.0320. Okay, evidently I like to make these hard for myself. So literally, I don't need the inverse sine, right? Because remember, for small angles, the inverse sine is the same as the sine. If you're in radians, for small angles, the sine of the angle is the same as the angle in radians. Okay, so 410 times 10 to the minus ninth divided by 0.032 times 10 to the minus third. And indeed, I get that half the angle is 0.0128 radians times 2 gives us 0.026525 radians. All right. What is the width on a screen that is 3.6 meters away? All right, we can do this. This will involve some trigonometry. Okay. All right. So I'm going to erase. Okay. Let's pretend that the screen is kind of a arc. Okay, let's do it approximately. So B approx. Okay, let's approximate V, right? Well, remember that radians are pretty simple things, right? So if we've got some angle like this, okay, and we've got some distance to it, which is going to be 3.6 meters. Basically, that angle is just S over L, right? But it has to be radians. We have to use the radians, right? So I'm going to go 0.0. It's 0.25625 is equal to that distance over 3.6. So I'm going to multiply this by 3.6. That should work. And indeed it does, right? So S is equal to 0.09225. So 0.922 centimeters, roughly, right? Notice there's a 5, so really you'd round it to a 9.23 centimeters, right? Okay, so that's one way to do it. Okay, the other way to do it is that you just don't believe in all of this stuff here. So we're going to use that angle there, which we figured out was in degrees, was this angle here is 0. Whoops. That angle, half that angle is 0.73412 degrees, right? Okay, so I can find, legitimately, I can find that distance, half the distance, right? Okay, half of this angular width, I can find that with the inverse tangent, right? Okay, so this is 3.6, and this side here is going to be, S is going to be, or the opposite side, right, is going to be 3.6 tan of 0.73412. Okay, that's just ordinary tan, right? So, so I'm going to go 3.6 times tangent of that guy. And I get that it's 0.461 meters multiplied by 2 because it's the full width of that central peak, right? So you only do 2 of those. We're going, so I just figured out this angle to here, right? The distance is, we want to figure out that distance. So multiply by 2. And I get 0.092257 centimeters. Okay, so really maybe that should be a 3 right there. Okay, what distance separates the central maximum from the next maximum on a screen 7.1 centimeters away? Ooh, the central one to this guy here. Okay, let's do this. So here's our central guy right here. That's going to be at 0, and then there's this one, right? Well, that next maximum kind of falls in between there. Is it 1.5 wavelengths away? I think it is, right? Okay, so that angle is going to be 1.5 times lambda over d, right? And that's because the minimum here is lambda over d. The next minimum is 2 lambda over d. So that guy is going to be right in the middle there, okay? So let's do the approximate thing, and I'll leave the exact thing up for the rocket scientists here. Okay, so that angle is literally going to be in radians, 1.5 times 410 times 10 to the minus 9th divided by the distance of the aperture is 0.032 times 10 to the minus 3rd meters. I always use the 7.10. That shows you how spacey I am. Now remember this D here they're talking about here, that's the width of the slit, not the distance to the screen. It wouldn't make sense. Okay, so 1.5 times 410 times 10 to the minus 9th divided by 0.032 times 10 to the minus 3rd is the angle in radians is 0.0192 radians, right? And then that distance is just simply going to be theta is equal to S over L, right? So that equals whatever that distance is divided by L is 7.10. So multiply this by this, right? So times 7.1, and holy cow, I get the right answer. I get S is 0.136 meters, or S is 13.6 centimeters, right? Now, obviously, you could take that angle and figure it out. You could figure out what that angle is. You could find the inverse sine of it, right, and get what the actual angle is, and then you could do the tangent and all that stuff, right? But you're gonna get the same answer, okay? And this video is already like 50 minutes long, so I'm just gonna stop.